This is the MAT125 Lesson 10 on mathematical induction. In this lesson, we'll look at two examples of mathematical induction. The first example, number 1, says prove 1 plus 3 plus 5 plus 7 plus continuing up to the number 2n minus 1 is equal to n squared. So this is a neat little pattern. Let's take a closer look at it. So maybe to be a little bit more formal, I should have written it prove for any n elements of the natural numbers that this equation is true, because I really mean only the case that n is a natural number that is 1 or 2, 3, 4, 5, and on and on and on. Maybe you don't have to put the n element of the natural numbers because we often indicate we're talking about natural numbers if the equation involves the letter n in a formula. We're implying natural numbers, but it's good to be a little bit more precise and formal and say that this is specifically for natural numbers. Okay, so this is, as you can see, summing up an arbitrary number of odd natural numbers, and the answer, it says, is equal to n squared. This is kind of a neat little pattern that we can illustrate the pattern, I think, in a really kind of neat way. Let's say we start with just one dot. Here's one dot. If I now add to that 3 dots, and I do this in a careful pattern that looks like that, I now have 4 dots, which is 2 squared. And if I now add on 5 dots, if I add another 5 dots, 1, 2, 3, 4, 5 dots, I now have 3 squared, and that's 9 dots. Do another one. If I add on now, I'm going to add on 7 dots. So this is 1, 2, 3, 4, 5, 6, 7 dots. So how many dots do we have total? It's 4 by 4, it's 16 dots. So sort of the pattern has been started with a 1, I added 3, and then I added 5, then I added 7, and it kept getting squares. And the square I got was basically the number of dots that I have on a side, right? So there's 1, 2, 3, 4 dots on a side and 4 dots on this side. The square is a n by n square, and it's equal to n squared. So this seems like it would just continue, right? If I did the next number in the sequence, it would be 5 by 5, and it would be 25, right? If I added the first 5 odds, I should get 25. If I added 1 plus 3 plus 5 plus 7 plus 9, see, that's 4 plus 12 is 16 plus 9 is 25. And sure enough, that would be 5 squared. So looking at this continuing to be true may convince you that it's always true, but it isn't really formally a logical proof of it. It's just evidence. This is really like inductive reasoning. We now can make a theory that this would always be true, but we haven't really proven logically that it's always true. And also, what I'm going to present is this mathematical induction, is this sort of logical general principle that would work in any of these types of situations where I wouldn't necessarily be able to draw a figure to reason from the figure, right? I want to have some logically sound general principle that is always true that I could bring to bear in a particular example such as this one and show that this must be true based on something more general that's always true. Even in fact, the principle of mathematical induction itself can be proven from more basic fundamental principles like the well-ordering principle of the integers, but we'll just start with the principle of mathematical induction itself is a general principle that is always true, that is generally true, that we could use in particular examples like proving this formula. So the principle of mathematical induction is this general principle that says, given some statement P of n, really some predicate that is true or false for a particular value of n. Let's say p of n is some property that's defined for the integers n, where, okay, it doesn't have to be positive. You can have integers. Let a be some fixed integer, and suppose the following two statements are true. Let's show that p is true at a, sort of what we call the base case, that it's true at that case, and then we'll also, if we can establish that for any integer k that is equal to a or bigger, if the statement is true at k, then it must also be true at k plus 1. If we can show that's true, then taken together, we could then logically conclude that the given statement would be true for all values of n greater than or equal to n. Greater than or equal to a, I'm sorry. For all values of n that are greater than or equal to a, the statement p of n would be true, logically must be true. My sort of intuition as to why this principle is true generally sort of goes like this. I imagine this infinite ladder that I want to show some property p is true at every single step on this ladder on forever. So I think of it like, if I could establish that we could get on the ladder at some base case, some initial rung, if you establish that you can reach one of the rungs, the sort of a base rung, you can establish first that you can get on the ladder at one of the rungs, and then you can separately establish that at any rung, if you happen to be on an arbitrary rung, then from that rung you could get to the next one. Well, those two things together say that I could reach any rung on the ladder. In other words, if you can get on the ladder, and if you're on the ladder, you can get from one rung to the next, okay, then I can reach every rung on that ladder on forever. So I know that this statement is true for every single possible point on that ladder forever. So let's see how that applies in this particular example. We could state the formula as a predicate like this. It was the sum of the odds, sum of the first n odds. So we're using 2n minus 1 so that when we plug in, let's say, for example, n equal to 1, we end up with the first term in our sum is when there's one term. Right? When n is 1, you get this one. When n is 2, you get 3. If n were 3, you'd have 2 times 3, and that's 6 minus 1 gives you 5, so that's the third odd. So this is an odd value that follows each of the previous odd values, and we're saying the statement is that summing up those n arbitrary odd values gives you the number of values squared. So all we have to do is establish that it is true at a base case, and the base case in this example would be showing that it's true at 1. So I want to confirm that when you plug in 1, it's true. Of course, 1, when you plug one term, when n is 1, this statement is definitely true for 1, because if you plug in 1, you get just 1 equal to 1 squared. So usually the base case is an easy thing to establish. Where the challenge comes in showing that if it were true at an arbitrary value, that it would have to be true at the next arbitrary value. So what we're going to do is we assume it's true at k. Just assuming that if it were true at k, all we have to do is show that it would be true at the next step. So what I mean as I'm writing this is that when I say assume p of k, I mean assume p of k is true, and then show p of k plus 1 is true. So p of k is some arbitrary k, some arbitrary integer bigger than 1, so that is some natural number. So that would be 1, would be the first k odds. So 1 plus 3 plus 5 plus, this would continue up to 2k minus 1. That would equal k squared. Now we're going to use that. Assuming that's true, all I have to do is show that it would have to be logically true at k plus 1. So the statement k plus 1 what you have to do now to show something is equal is you cannot use that it is equal to show that it's equal. So I have to start with the left-hand side of an equation, get to a right-hand side of an equation. So let's see how that might work out in this case. So pk plus 1, starting on the left-hand side, is the sum of the first k plus 1 odds. So we'd say 1 plus 3, 5, and it would go up to k plus 1, but before you get to k plus 1, you get to k, and you really want to include that term before in order to be able to use the information that we already know is true here. So let's put plus 2k minus 1 plus 2k plus 1 minus 1, because that's what you get when you plug k plus 1 into this statement P. If you'd have to put k plus 1 in where there's a k or where there's an n. Now this is just the left-hand side. I want to show that it's going to equal to this k plus 1 squared, and I'll get that to in a minute. So this left-hand side, now I've already established that this is equal to k squared. So I can use that. That's part of what's called the inductive hypothesis, the fact that we're assuming it's true at some arbitrary value, only just there, and just from that, assuming that it must be showing that it must be true at the next value. So we can use that inductive hypothesis to say this is k squared, but then we have this 2k plus 2 minus 1. I just distributed the 2. That's k squared. Plus, well, that would be 2k plus 1 if you simplify. And of course that's going to factor, which I want to do to say equal to. So I've used that inductive hypothesis, that 1 plus 3 plus 5 plus adding up to 2k minus 1, the sum of the first k odd numbers. I've used that that's equal to k squared. Then I distributed this and created and then realized algebraically that it's equal to k plus 1 all squared. So this left hand side equals this right hand side, and that is the statement P at k plus 1. And so then we can say, by mathematical induction, the sum of the first n odds is equal to n squared. And that would be true for any natural number greater than or equal to 1. Let's have a go at one more example. Prove for any natural number n, the sum of the first n cubes is equal to this formula, which happens to be the sum of the first n natural numbers all squared. It's kind of an interesting pattern right there. Before we prove it, let's just look at a couple of examples. Take 1 cubed plus 2 cubed. If you add 1 plus 2, that's 3, and you can get the answer with 3 squared. That's equal to 9, right? Which is 8 plus 1. Let's try another one. Let's add the first three cubes. Right? 1 cubed plus 2 cubed plus 3 cubed. So just add the bases. 3 plus 2, that's 5. Plus 1, that's 6. So do 6. Now that was a cube. 3 plus 2 is 5 plus 1, that's 6. So 6 squared is 36. And what do I have here? 1 plus 8, that's 9, plus 27, which is 36. One more. So according to this formula, what I could do is just add the bases. 4 plus 3 plus 2 plus 1. Just adding the first n integers and then squaring that, which is what this is saying. So that's 3 plus 3, that's 6 plus 4, that's 10. So this should be 10 squared. That's 9 plus 36. All this is adding up to 36. Plus this is adding 64. Yep, that's equal to 100. So the fact that it checks off in a few examples, of course, is no proof that it would generally work all the time. And that's what our mathematical induction is going to do. Is a general principle worked in the previous one, will work in this one. If I want to prove a statement is true for all values from a certain base value, all on from then on, um, and there are some integers from some point on, I can use this principle of mathematical induction. So we need to establish that what is our statement that we're trying to prove. The statement would be Pn is basically the formula. 1 cubed, 2 cubed. So all of this stuff up here was just some examples to look at the pattern that was interesting how that pattern worked, but now begins the proof. So I will create the statement P of n that I want to show is true. I want to show that it's true at some particular base case, and I'm going to choose showing that it's true at 1. So let's see if it's in fact actually true at 1. If you take n to be 1, then you just get 1 cubed on the left hand side, and separately on the right hand side, if you plugged in 1, you'd have 1 times 2 divided by 2 all squared, but of course that's 1 squared, which is 1, so the statement is true when n is 1. Now this is sort of like my step. My second step is to take the inductive hypothesis that it is true at an arbitrary value k, and then using that show that it would logically have to be true at the value k plus 1, that the statement would have to be true at k plus 1 if it were true at k. So let's just write down the case that it's true at k, my inductive hypothesis. You just plug in k everywhere there's an n. I want to show that this is true, p of k plus 1, which just to maybe show the target at which I am trying to hit. What is it that I really want to show true? I want to show this statement is actually true with k plus 1 plugged in everywhere there's a k, and to do that I can assume that it was true at k, at the value right before k plus 1. So I really want to show 1 cubed and 2 cubed and 3 cubed up to k plus 1 cubed is equal to, and replace k plus 1 everywhere here. The formula was that it had to be squared here. I wrote that wrong. This is the statement at k plus 1. I want to show that's true, and I can use this. And so this we call this the left-hand side, and I'll call this the right-hand side. And of course, if I'm trying to show this is true, I wouldn't use that it's true, but I can use that this one is true, just up to k. And that means the term right before this, I know something about what that's equal, and of course that's what you need to use. So to show kind of like overall what I'm trying to do, I'm going to take the left-hand side, write down what that is, and show that I can transform that into the right-hand side without using the right-hand side. Right? So I know the left-hand side is 1 cubed, 2 cubed, 3 cubed, and if it's going to go all the way to k plus 1, it would have to have the k cubed right before that, so this would be plus dot 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 up to k cubed, and then the k plus 1 cubed. And that's just the left-hand side. But because of the inductive hypothesis, right here, if you added the sum of the first k natural numbers cubed, you would get this quantity squared. So let's use that. By the inductive hypothesis, this is equal to k plus 1 all over 2 all squared. So this whole thing right here turned into this. And I just copy down the k plus 1 cubed into the next line. Now you might be wondering, are we supposed to multiply this out? Where are we going to go with this? Well, keep in mind what the target is. I'm basically trying to get it to equal to this right-hand side. And so I don't really necessarily need to multiply it out, although you could. What's a little more efficient here is to notice that you could factor it, because essentially that's the form I have on the right-hand side. So if I notice what is it that you could actually factor, let's take one extra step. Let's put this, it would actually look like this. I mean, we could write it this way, and it helps me a little bit better to show. What I want to do is factor out the k plus 1 squared out of both terms, because both of these terms have a k plus 1 to the power 2, since this has 3 of them. So just factoring out k plus 1 squared, we'd have k squared over 4 plus k plus 1 to the power 1, like that. Let's get a common denominator here. Let's combine these two terms. Let's factor this trinomial. That is the right-hand side. Way back here, I kind of wish I had simplified that to just say k plus 2. So I'll do that here. When we plugged in k plus 1, we get k plus 1 plus 1, so we get k plus 2. So k plus 1 and k plus 2 product all squared over all divided by 2 and then all squared. That was the right-hand side. There it is. So let's state the result, the conclusion, in terms of the arbitrary natural number n. 1 cubed plus 2 cubed, 3 cubed. If you add natural numbers cubed up to some arbitrary value, it's going to be n times n plus 1 divided by 2, which happens to be the sum of the first n integers. It's all squared. Okay, so there we have it. We've proved it for any value n greater than or equal to 1. That's the end of my video. I hope it's been helpful.